In this lesson, we will derive the Reynolds transport theorem. In introductory physics courses, the three major conservation laws, conservation of mass, conservation of momentum, and conservation of energy, are usually described using the system point of view. The conservation of mass states that the amount of mass m in an isolated system is constant in time. At t1, we observe a chunk of fluid. At time t2, the fluid may have moved, deformed, and even broken into multiple pieces. But if we are tracking all the particles in the fluid the entire time, the mass of the system at time t1 would equal the mass of the system at time t2. The conservation of linear momentum states that the time rate of change of a mass's momentum, which is mass times velocity, is equal to the sum of the external forces acting on the mass. Here is a ball that has a certain momentum at time t1, and two forces are acting on it, F1 and F2. The net effect of these forces are to push the ball forward and downward. At time t2, the momentum has increased in both of these directions. The conservation of energy states that the time rate of change of energy E of a mass is the sum of the rate of work and heat transfer. A mass has energy E cis at time t1. Energy can flow into or out of the system through work or heat transfer. At a future time t2, the system may possess a different amount of energy. Notice that the conservation laws involve the time rate of change of an extensive property. An extensive property of a substance is a property that is proportional to mass. That is, if you double the system, you double the property. The three extensive properties in the conservation laws are mass m, momentum mv, and energy E. Let's factor out the mass from these three properties. Mass can be rewritten as m times 1, momentum can be rewritten as m times velocity v, and energy can be rewritten as m times the specific energy, lowercase e. The specific energy is the total energy per mass. By factoring out mass, we have written the three extensive properties as the product of an extensive property m times an intensive property. Intensive properties are independent of mass. For example, if you double the mass of the system, you do not double the velocity or specific energy. For the rest of this lesson, we will refer to any extensive property as capital B and the corresponding intensive property as lowercase b. Capital B will represent mass, momentum, and energy. And notice that we can get the intensive property lowercase b by dividing the extensive property capital B by mass. Let's examine an arbitrary control volume that is not deforming. We will assume that a system coincides with the control volume at time t. The control surface surrounds the control volume and is marked by the red dashed line, while the system is represented by pink shading. We will observe the control volume from a reference frame that is attached to the control surface. If the fluid moves relative to the control volume, the system will flow out through the control surface and new fluid will take its place. The resulting velocity field is the fluid velocity as observed from the control volume. At an initial time, t, the amount of extensive property capital B in the system is equal to the amount of extensive property in the control volume because the system and control volume coincide with each other. If the use of the symbol capital B is confusing to you, you can think of capital B as mass. At a future time, t plus dt, the amount of extensive property in the system may be different from the amount of extensive property in the control volume. Notice that the system has left region 1 and moved into region 2, but there still remains some extensive property in part of the control volume, a region indicated by CV minus 1. We label 4 points on the control surface, A, F, C, and D. The inflow region of the control surface is AFC, and the outflow region of the control surface is ADC. The time rate of change of an extensive property in a system is equal to the amount of extensive property at time t plus dt minus the amount of extensive property at time t divided by the small time dt. Substitute the expression for bsys at time t plus dt. At time t, bsys is equal to bcv. Next we group the bcv terms. Now there are three terms on the right-hand side of the equation. We will analyze them one at a time. First, we examine the terms with B1 and B2. Recall that region 1 is the space in the control volume vacated by the system at time t plus dt. It is where new fluid enters the control volume through the control surface. Region 2 is the space outside the control volume that is occupied by the system at time t plus dt. B1 refers to the amount of extensive property in region 1, and B2 refers to the amount of extensive property in region 2. At time t, the entire system resides in the control volume, so regions 1 and 2 do not exist yet. Therefore, the amount of extensive property in those regions at that time is 0. Since any quantity minus 0 is equal to the original quantity, we can rewrite B1 at time t plus dt as B1 at time t plus dt minus B1 at time t. This is the rate that the extensive property changes in region 1 due to the influx of fluid through the surface AFC. We will rewrite this term as Bn AFC dot. Similarly, we can rewrite B2 at time t plus dt as B2 at time t plus dt minus B2 at time t. This is the rate that the extensive property changes in region 2 due to an outflux of fluid through the surface ADC. We will rewrite this term as B out ADC dot. We can derive expressions for B in AFC dot and B out ADC dot by taking a closer look at the influx and outflux surfaces. We start by examining a small piece of surface area dA on the outflux surface ADC. The velocity vector v and the normal vector n hat are shown. The angle theta between the two vectors is always less than 90 degrees because n hat always points perpendicularly out from the surface and the velocity vector always points outward. If the velocity vector pointed inward, it would indicate a region of influx. Zooming in closer to the area dA, we see that an oblique cylinder of fluid of mass dm and volume dv would flow out from the surface during the small time dt. This cylinder would be extruded in the direction of the velocity vector and would contain a small amount of extensive property dB. The side of the cylinder dl equals the rate the cylinder is extruded, which is the velocity vector v, multiplied by the amount of time the cylinder is extruded, which is dt. D capital B can be rewritten as the intensive property lowercase b times dm. And dm can be rewritten as the density rho times the volume dv. The volume of an oblique cylinder is the area of the base dA times the height of the cylinder as measured in the direction normal to the surface, which we will call dln. From geometry, dln is equal to dl times cosine theta. The side dl is equal to the velocity times dt. And now we plug in the expression for dv back into the equation for d capital B. Dividing dB by dt gives us the rate the extensive property flows out of the small surface area dA. We can eliminate dt in the numerator and denominator and rewrite v cosine theta as v times 1 times cosine theta, which is equal to the magnitude of the velocity vector times the magnitude of the normal vector times cosine theta. This expression is equal to the dot product of the velocity vector and normal vector. So now dB dt is equal to lowercase b times density times the dot product of the velocity vector and n hat times dA. We will label this quantity as b out dA dot to emphasize that this is the rate the extensive property capital B flows out from the area dA. We can find the total outflux of extensive property B through the region ADC by integrating B out dA dot over the entire surface area ADC. The total outflux is equal to the intensive property little b times the density rho times v dot n hat times dA integrated over the entire surface ADC. If we conduct a similar analysis on the influx region AFC, we would find that the expression for the rate of influx through surface AFC is negative little b times rho times v dot n hat times dA integrated over the area AFC. The negative sign results from the fact that the velocity always points inward and n hat always points outward, so the angle between them is always greater than 90 degrees. We are now able to rewrite the first two terms in the following manner. b2 dt at time t plus dt minus b1 dt at time t plus dt is equal to b out ADC dot minus b in AFC dot. This expression represents the net outflux of extensive property capital B from the control volume. We plug in the expressions we have just derived for the two terms and multiply the two negative signs together to create a positive sign. Since we are adding the same integrand expression over two separate areas, we are able to combine the two integrals into one. Now we have the integral of little b times rho times v dot n hat times dA, with the limits of integration being the entire control surface, which is the region marked by red dashes. There is one more term to analyze in the equation for dB cis dt. The amount of extensive property in the control volume at time t plus dt minus the amount of extensive property in the control volume at time t divided by dt. This can be rewritten as dBcv dt and is the time rate of change of the extensive property in the control volume. The total amount of extensive property in the entire control volume can be determined by adding up the small amount of extensive property that exists in the many small fluid elements that make up the control volume. The volume of each fluid element is dV and contains a small mass dm and a small amount of extensive property dB. We will assume that the fluid elements are so small that the density rho is constant within the entire fluid element. However, density may vary between different fluid elements. We can rewrite d capital B as lowercase b times dm. And dm can be rewritten as rho times dV. Now take the derivative of this expression for bcv. Putting everything together, we have an equation for how an extensive property in a system changes in time in terms of quantities that are related to control volumes. The time rate of change of an extensive property in the system is equal to the accumulation rate of the extensive property in the control volume plus the net outflux rate of the extensive property through the control surface. This is the Reynolds transport theorem. Traditionally, the lowercase d's on the left side of the equation are replaced with uppercase d's to highlight that we are examining the time rate of change of an extensive property in a system. The derivative on the left side of the equation is often called the material derivative. And it is important to remember that the velocity vector in the equation is the fluid velocity relative to the control volume. Although the Reynolds transport theorem is a very important equation in fluid mechanics, in practice, fluid mechanics problems are rarely solved by directly applying the equation shown on the screen. Instead, the Reynolds transport theorem is used to derive equations for the conservation laws for control volumes, and it is those derived laws that are used to solve problems. We will discuss the conservation laws for control volumes in future lessons. Most control volumes in fluid mechanics are non-deforming. However, if the control volume is deforming, you would need to take into consideration that the control volume and control surface change in time when performing the integrations. Many devices, such as pumps and jet engines, are designed to operate under steady flow conditions. For these type of scenarios, the influx rate of the extensive property exactly balances the outflux rate, and there is no accumulation of the extensive property in the control volume. In other words, the amount of extensive property in the control volume is constant in time. And as a consequence, the first integral on the right side of the Reynolds transport theorem becomes 0.